Welcome back to our heat transfer class, where we are delving deeper into the fascinating world of thermal energy exchange. This video was made with the support of InnoEnergy. Remember that the introduction to heat transfer is divided into several lessons. In this fourth lesson, we're about to unlock the secrets of how heat is transferred when temperature differences come into play. We're going to answer the burning question raised in our first video, how the process of energy transfer takes place when there is a difference of temperature inside a system or between systems.
The first phenomenon to address is the diffusion of kinetic molecular energy. As the temperature of a solid increases, the kinetic energy of its molecules also increases, causing them to vibrate more vigorously. In this scenario, when the left-hand side of a solid structure is heated, an interesting phenomena occur. The atoms and molecules in the left hand increase their movement, and as consequence, the temperature rises. Neighboring molecules increase their degree of vibration, so energy diffuses from each layer to the neighboring layer. As a result of the transfer of energy, the temperature also increases. And energy is transferred from the points or surfaces at higher temperature to the ones at lower temperature. By isolating the solid from the outside, there will come a time when all the molecules will have the same vibration and, therefore, the same temperature. This principle is similar to the diffusion of matter. When you put a drop of dye in the water, the dye diffuses slowly into the water. After a while, the dye is evenly distributed in the water. Diffusion is essential to understand how heat transfer works and why solids left in contact with each other at different temperatures will tend to reach a state of thermal equilibrium. However, the diffusion of kinetic energy is not the only physical phenomenon that occurs when the solid has a metallic structure. In the metallic structure, there are delocalized electrons. When one side is heated, electrons in this area gain kinetic energy. Their migration to colder parts enhances the rate of heat transfer. As a consequence, metallic materials are more conductive than non-metallic ones. We will call conduction or conduction mechanism the transfer of heat within material media by diffusion of kinetic molecular energy or by electronic migration. The second phenomenon to address is the transfer of energy on the surface of a solid in contact with a fluid. Unlike solid bodies, fluids are characterized by having movement and mixing inside. We will call convection to the mechanism of heat transfer when at least one fluid is involved. Generally, but not exclusively, convection will take place on the surface of a solid in contact with a fluid. Depending on the driving force for the movement of the fluid, we can distinguish between free and forced convection. Free convection is due to the recirculation of the fluid when there is no external force that drives it. In the campfire in the figure, the heated air decreases its density and, due to the effect of gravity and buoyancy forces, tends to rise. At home, the fluid surrounding a heat source becomes less dense and rises. The cooler surrounding fluid moves to replace it, forming a convection current. This phenomenon is responsible for convective currents in nature. Free convection also produces thermal winds in the seaside. However, free convection is also a slow phenomenon. In industrial applications, the circulation of the fluid is carried out by pumps, compressors, blowers or fans. We call this forced convection. At home, a fan increases the circulation velocity of the air, providing some comfort. And a fan can improve an electronic chip cooling by increasing the air velocity on the heatsink surfaces. This is used, for instance, in the refrigeration of electronic integrated circuits. In forced convection without phase change, the fluid circulates in layers near the solid surface. Theoretically, there is not mixing of matter between layers. When the fluid velocity is high, turbulence may appear. Above these layers, the fluid velocity and its temperature are not influenced by the interaction with the solid surface. If the solid surface is hotter than the fluid, or colder, the temperature difference acts as a driving force for heat transfer. Because the fluid layers do not mix with each other, heat transfer takes place by diffusion. In the turbulent zone, the movement and mixing of the fluid drives the transfer of energy between hot and cold zones. The bulk movement of the fluid is named advection. Convection is the most complex mechanism since it combines kinetic molecular diffusion or conduction within the fluid, with the transfer of energy due to the mixing of the fluid layers at different temperatures, or advection. The third phenomenon to address is the transfer of energy when there is no medium between surfaces. All surfaces at any temperature emit energy in the form of electromagnetic waves. The most obvious experimental evidence that this occurs is the energy we receive from the sun through a vacuum. Waves travel through a vacuum until they hit another surface. You can also experience the radiation coming from a campfire or the flame of a cook stove. In this example, the higher temperature surface emits more radiation than the cooler surface. The net balance will result in a transfer of energy from the hottest to the coldest surface. The same thing that happens between the sun and the earth. At home, or at industrial scale. Radiation also is transmitted through transparent media such as air. Radiation is the fastest heat transfer mechanism, since it propagates at the speed of light. Open question. What heat transfer mechanisms can you identify in a pot where water is boiling? Stop the video here and try to answer this question. Were you able to answer the question for yourself? There is radiation from the flame to the bottom of the pot and convection between the hot gases and the bottom of the pot. Conduction through the vessel walls. The free convection of the liquid inside the container. The convection of the vapor produced on the surface of the liquid. The convection between the walls of the container and the outside air. And radiation between the vessel walls and the surroundings. Don't miss the videos about the rate equations for each heat transfer mechanism.